Hello, welcome back to the One Human video series. This will be the first of several videos I do on solar energy and renewable energy in general. I've been studying that topic for about 15 years now. It's been the primary focus of my academic research. And I think there's a lot that's misunderstood in the public's eye. There's a lot of solutions related to it that are not fully appreciated because of the lack of understanding. And so I've tried to break it down, the topic, into short snippets so that the mainstream, the viewers, can begin to understand the topic and can hopefully advocate for increased investment and increased activity in this area. So let's get going with the slides. Okay, so the central question of this video is, do we have enough sunlight to power everything that humans do? And what humans do, of course, is we move around. We use things in our homes. We heat our homes. We pump water into our homes. We cook things in our homes and so on. So do we have enough sunlight to do that? And the answer is actually yes, despite maybe some other things you have heard. And I will address and show you how this is done. So let's jump in it. This slide shows the incoming solar radiation on various parts of the United States. And we measure that through something called the annual average solar energy. And as you can see, there's dark red regions in the southwest and lighter regions in the north and the northeast. And I'm going to blow up that key and so you can see what those numbers refer to. And it may be a unit you're not familiar with. Kilowatt hours per meter squared per day. And a kilowatt hour is just a measure of electricity or energy. And meter squared is exactly what it says, a meter by meter. And then a day is a day. So the question is, how much solar energy impinges on these locations over a meter squared in a given day? And you see the numbers range from above 5.75 to less than 4 in some parts of the United States. A better unit, which is actually equivalent to this, is what many energy scholars use. And that is to say that one of these kilowatt hours per meter squared per day is actually equal to one full sun hour. And you'll see why we use this fairly convenient equality to say that's a full sun. One of these is a full sun. So as you can see, some parts of the United States will get close to 6 or more full sun hours in a day, and some places will get less than 4. Let's go back to the original and notice, let's focus on Illinois, where I live. And you'll see the numbers here are in the, not the lowest values at 4. Less than 4 would be in northern Wisconsin or Alaska. This would be between 4.2 and 4.5 kilowatt hours per meter squared per day, or the equivalent of 4 to 4.5 total sun hours, full sun hours every day. And of course, this accounts for the fact that it's not sunny a lot of the days. It takes into account clouds. It takes into account a lot of different things that might affect it, including nighttime. So clearly there are days that are longer than 4 hours in Illinois, but in terms of this full sun measure, it accounts for all of these variations, and you'll see how valuable it is. And it does show the variability. So Illinois is somewhere between 4 to 4.5, whereas places in New Mexico, most of New Mexico, exceeds 5. So that might make you think that you have to live in New Mexico to get enough sunlight. That's where we're focusing on Illinois, which is more kind of a national average. Is anyone taking advantage of this resource? Well, let's see. This is an article from January 4th of last year looking at the incoming project in our county. Knox County is the county of where Galesburg is the county seat. And we are looking at a project of 50 megawatts on 360 acres. And that's going to be a solar array. This is photovoltaic array, similar to what you may have seen, particularly if you've seen on top of homes or on countrysides. This is what we're looking at. But this is a very large project, and one that, as you see, could have huge investment in our community. But from these two numbers, the megawatts, which is a power term, and the number of acres that this particular farm will take up, we can calculate what's called a power rating. It's very easy to do. We just take the power, which is 50 megawatts, and we divide by the area. When we do this, as shown, we can get a number. So 0.14 megawatts per acre. And we can use that as a reference point. That's how much power we anticipate getting for a solar farm located actually anywhere. This is not specific to Illinois. This is based on the farm itself, the size of the farm, the number of panels and such. As you'll see, the number of hours that the full sun hits these panels is going to have is going to decide how much energy we get. So 0.14 megawatts per acre. That number will become important later on. Let's talk about Illinois for a moment. So Illinois is a very large state, 56,000 square miles, in fact, of land, has a few thousand miles of water as well. And that works out to about 36 million acres. That's how many acres. And an acre may be something unfamiliar. An acre is about the size of a football field. So this gives you an idea of how big Illinois is. Of this land, about 7% is urban or built up. So you're going to find buildings and parking lots and humanly active areas. About 4% are wetlands still in Illinois, which are generally used to cleanse the water and so on. And what's left? Well, the majority of what's left is agricultural. About 75%, 3/4 of the land, 27 million acres of Illinois land is agricultural. And as this project that I just referred to is going to go on what is now currently used for soybeans and corn, most of these larger arrays, solar arrays, are going on agricultural land. So one more thing to cover before we piece all these different things together. Metric prefixes may be something new to you. I need to describe the difference between a kilo, a mega, and a giga. So most people are familiar with kilo. Kilo is 1,000. So a kilogram is 1,000 grams. A mega is really just 1,000 kilos. So a megawatt is 1,000 kilowatts. A gigawatt is 1,000 of those. And so a gigawatt is 1,000 megawatts. Or in fact, it would be 1,000,000 kilowatts. So these are all numbers that come into play because we're going to be talking about large numbers in a minute. So how much usable sunlight hits Illinois ag land? Well, this is what we're looking for. We want the total insolation or energy available to us at ground level. Well, we use this equation. It looks complicated, but it actually isn't when you think about it. We have the land area, which obviously is going to be relevant, the amount of sunlight, the efficiency of the technology, and then the amount of time that these panels are going to be operating. Another way of looking at that equation, given some of the terminology I'm using here, is land area times full sun hours per day, which you should know the number now, the power rating of solar, because that's the type of technology we're using, and then the time in a year. How much time is in a year? So the numbers we've seen in this video, 27 million acres multiplied by the average of Illinois is about 4.2 sun hours per day, multiplied by 0.14 megawatts per acre, the power rating. And then the number of days in a year is 365. And you might be wondering why we're using days here, not hours. Well, if you look at the units of these four variables, you'll see that acres is going to cancel, hours is going to remain, days are going to cancel, and megawatts is going to remain. And so we're going to actually have megawatt hours divided by year. So a megawatt hours per year, when we do the math, and you should check this math, we get 5.8 million gigawatt hours per year. And this is the number. Now, that's not a number most of us know what that means, but you'll see in a minute, we can use that to compare. So this is the amount of energy that is available to us. In theory, if all of our farmland was used for solar energy production. Now, of course, we need to have food as well. So as you'll see, we don't need to use nearly that much, but this would be the potential. Well, how much do we use? Okay, well, you have to go and look this up. The total energy consumption in Illinois, I'll give it to you in a minute, but the number I'm looking at here is electricity, and it's all electricity. So it's not just residential, but it also includes commercial, industry, as well as a very small amount for transportation at this point, this new electric cars and buses that are coming into play. Residential, should be noted, is about 35% of that total. But we're looking at the total, and the total is a number. You can look it up. For 2020, I show you the source. The number was 132 million kilowatt hours. And using the conversions that I showed you, you can convert that to 132,000 gigawatt hours. That's how much electricity we use in Illinois on a given year, particularly 2020, which is a pretty good reference frame. So how does the potential production that I showed you 2 slides ago compare to this consumption? Well, here are the two numbers side by side. We found that we're using 132,000 gigawatt hours, and we have the potential to produce 5.8 million gigawatt hours. Obviously, the number in the bottom is bigger than the number in the top. And how much bigger is it? Well, it's about 44 times larger. So there is solar energy available to produce 44 times more than we need at current usage rates. Well, you can do the reciprocal of that 44, and you get about 2.2%. So using 2.2% of Illinois ag land for solar would provide 100% of all Illinois' electricity needs. Now that might seem a lot to you or little. It's actually a fairly small amount. We'll get in future videos, we'll look at how much land is used for coal and some other energy sources in our state and elsewhere. 2.2% to provide all electricity of the land would be necessary for 100% electricity. And of course, this assumes we're not using wind for any electricity or hydropower or nuclear or any other source, just solar energy alone. Future videos will get into this other energy sources and the way they might provide and assist in providing us sufficient energy. As noticed, as mentioned previously, I'm going to provide a book recommendation. This is a new book, just came out this year. It's written by Mark Jacobson, a Stanford professor, one of the most well-known researchers on renewable energies in the world. And no miracles needed. How today's technology can save our climate and cleaner air. Very provocative title, something I think most of us would want to take a look at. I've read most of this book. It's been my summer reading, and I'll be using parts of it in my upcoming class next academic year. But it's an important read, and it's one that's accessible. It's not, there's some technical parts that probably are beyond some people, but for the most part, the bulk of it is accessible to most of you watching this. And so I encourage you to take a look at it. And that's it for today. I'll have a lot more to say about renewable energy and solar in future videos. Thanks for coming, and hope you enjoyed it.